Alright, welcome to lesson 11. We're going to be solving polynomial equations graphically. This is very similar to what we did in Unit 1, where we solved systems of equations with quadratic functions. And while we're going to be looking at equations with higher degree polynomials, the points that we're looking for are still the same. We're still going to be looking for points of intersection, which are the solutions to a system of equations. Okay, so to get us started, here's a situation. So go ahead and sketch out this graph and answer questions A and B in your notes, and then we'll discuss and see what we can learn from this particular situation. Alright, so we want to approximate the solutions to a system of equations that are graphed below. And as you recall, the solutions to a system of two equations are the places where each function has the same input and the same output. In other words, that's where they're going to be at the exact same point, meaning they're going to intersect. So if we're looking for those points, we want to approximate them. We're going to try and get as close to the correct x value for which they are going to intersect. So here we can see it's in between -4 and -3, closer to -4. So I might say -3.9. Moving on, over here we see that they are also intersecting. This is between 0 and 1, much closer to 0, so I might say 0.25. And then lastly, we have a point of intersection between 1 and 2, which appears to be closer to 2. So I'm going to say approximately 1.75. What we notice here is that we've gotten very, very close to the correct solution simply by looking at the graphical representation. And so we'd like to take advantage of this whenever we can by graphing the functions that we're dealing with and then using that graph to hone in on where the two functions intersect. Because sometimes we just want an approximation. We don't actually need the precise exact value. And in fact, if we want the precise exact value, your calculator or a computer program like Wolfram Alpha is going to be so much faster. However, when you look at a graphical representation, you'll want to quickly know what the solutions are going to be so that you can make decisions on the fly. Which function has a smaller x-intercept is actually a fairly easy question. X-intercepts, of course, the roots of the functions, and we want to know which one has a smaller one, meaning which one has the x-intercept that has the smallest absolute value. And while we can see all the places where the blue function intersects the x-axis, we actually know that the linear function won't intersect till farther on past +2. And so since the blue function has an x-intercept at -1, we know that that's going to be the function that has the smaller x-intercept. Alright, so let's go ahead and put what we've ascertained in words, and then go ahead and apply it to a couple of situations. Alright, so we've seen this definition before, but it's important to kind of always refresh our memory here. A solution to a system of equations, or the solutions to a system of equations, these are the x values for which f of x is equal to g of x. So if I have two functions, the x values where the two outputs, remember, f of x is function notation for the y value for this function, and g of x is the notation for the y value for this function, where those values are going to be equal. And so we've actually interpreted this in another way, which is to say that solutions to a system of equations, this really is telling me the point. I'm asking for the points of intersection. And I kind of always want to have that in my mind, that when I hear this phrase, what I'm thinking of are the points of intersection. So that actually when I'm reading a question and it says find the solutions to a system of equations, I'm actually annotating that and saying that I'm looking for the points of intersection. And that will really help me understand. there's a couple of examples that we've seen already that you might not realize actually correspond to this. So whenever we see a function, let's just call it f of x, and you're asked what are the roots, in other words, what will make f of x equal 0, this is a solution to a system of equations where your function g of x here is actually 0, right? In other words, the function that just runs along the x-axis, right? And that's why the solutions to this system are where the function intersects the x-axis. So we've really been solving this for quite some time, thinking about roots and where they intersect the x-axis. And now we're just going to be doing the exact same thing with functions of g of x, which are a little different than 0. Okay, so it's important to kind of always have that in the back of our mind, that we've done this over and over again and we can continue to do so. So how are we going to go about doing this? Well, we're looking for points of intersection. Graphical representation is really screaming at us. And so what we'd like to do is actually graph both functions. Once we have a sketch of both functions, we can start to pick the places where we think they intersect. So we can get pretty darn close, and what we want to do is just get as close as we possibly can. So we want to locate the points where the two functions meet or intersect. Okay, and so once we have that, in general, if we're just given a graphical representation, that's as far as we can go. But in some cases, we'll actually be given the exact functions, f and g. And so if we're given these exact functions, we can still sketch a graph, and we can still locate the x values where f and g meet. But we can take it a step farther if we are given the equations. What we can do is, if we are given the equations, we can actually plug the x values that we believe to be the solutions back into functions f and g to see if they're close to being equal to each other. And then we can actually change our x value a little bit to try and get f and g to be closer to each other. And we'll see an example of this in a second. But I want to mark down that this is something that we can do if given the functions explicitly. Alright, so if we have the equations, we are going to be able to test and refine our solutions. So these are steps that we should be pretty familiar with, but I want to make sure that we're just kind of always cementing in our head the protocol that we want to use when we're finding solutions to a system of equations. So let's go ahead and take a look at an example to help us kind of concretely see this in action. Alright, so here's the first problem. Go ahead and copy this down and try following the protocol that we just went through to the best of your ability to approximate the solutions to this equation. And then only once you've tried it on your own, go ahead and press play and we'll walk through it together. Alright, so remember, the first thing that we want to do is sketch the graph for each of these functions. And the function g of x is pretty simple. This is just a linear equation, a slope of 12 and a y-intercept of -10. F of x here is a cubic polynomial. So remember, if we want to graph the cubic polynomial, we want to find the key characteristics. We know it's a cubic polynomial, so the end behaviors, we know it's increasing to the right, decreasing to the left. And now we just want to find the roots here. How can we do that? Well, remember, we've talked a lot about how the roots are linked to the factors. And so if we factor this equation, we'll be in good shape. And it turns out we can factor out an x squared here, so we can rewrite this equation as x squared times 6x minus 5. And this will allow us to find the roots much more easily. First off, we know that to make x squared 0, we'll just have to plug in 0. So one of our roots will be 0. And the other will be that what makes 6x minus 5 equals 0. So if we solve that, and you can actually solve this in your head, if you set it equal to 0 and add 5 to both sides, you'll have 6x equals 5, and then divide by 6. So you'll have a root of x equals 5/6. So let's go ahead and sketch this graph out now. Alright, so I'm going to go ahead and use different colors here. I'm going to sketch the cubic polynomial first. So I have a couple of roots. The first is a repeated root at 0, and the second is a root at 5/6, and 5/6 is a little less than 1. So here we know the end behavior is increasing to the right and decreasing to the left. Now we know that since this factor here has a degree of 1, it's going to cross over the x-axis here, and then it really leaves me no choice. I've got to bounce off the x-axis here, and that's because this linear factor of x is squared. Okay, so that's a decent job, but you could be a little more accurate than me probably. And then what you want to do for your function g of x is go ahead and sketch this graph as well. Do this in red here. And this has a y-intercept of -10 and a slope of 12. So if you think about the slope of 12, that means when I move to the right 1, I'll go up 12. So I'll go up a little more than 10, somewhere around here. Okay, so there I've seen my functions, and now I'm going to try and approximate the solutions. So you can do this just by eyeballing. You can see it looks like they're intersecting here, looks like they're going to intersect right here, and they're going to intersect somewhere a little past 1 as well. So now you just want to approximate, and then you can actually test them out. So let's say one of our approximations will be when x is approximately -1. And then let's think about what these other two should be. So this appears to be somewhere a little before 1, and this appears to be a little after 1. And that should make sense because at 1, the function, the green function, should just be barely above the x-axis. But we know that our red function is going to be about 2 units above the x-axis. So we'll say something like maybe 0.9 and 0.11. 0.9, 1.1. Okay? And we can actually test to see how close we've gotten. So the way that we can test this is we can plug our x values into both f of x and g of x, and we can see how close we've gotten. And to do this, we want to make a little table here. So the table is going to have the x value that we're plugging in, and then the value of f of x at that point, and the value of g of x at that point. So let's try -1 first. What you should do is go ahead and plug in -1 into each of these functions, see what you get, and make a decision on whether you should go a little bit less, a little bit more, or whether you're confident in staying at -1. Also try plugging in 0.9 and 1.1. Alright, so here are the values that you get if you plug in the x values -1, 0.9, and 1.1. And what you can see here is if we look at them, we actually got really, really close. So when you plug in 0.9 for x, the y value you get for f is 0.03, and for g you get 0.08. It's only 0.5 difference, and so you feel really good. Like that's a very close answer. And if you wanted to try 0.8 or 1, you could see which one is getting you closer, and you could try and really hone in on it. With 1.1, we also get pretty close. We're about 1.3 away. And again, you could try plugging in 1.2, seeing if that got you closer. You could try plugging in 1.05 to see if that made the y values closer, and you could try and get closer that way. The one where we're a little bit off is when you plug in -1. If we plug in -1, we see that we get -11 and -22. And you think about, okay, well, what will get my cubic function to be closer to the value of my red function? And you know that the cubic is going a much steeper value. So if you went a little bit more to the left, the green function should slowly be catching up. So I encourage you to try plugging in -2. And if you plug in -2, you'll notice something that you still might not quite be there. So what I want you to do is I want you to try 2 more x values. You should have 2 more x values that you'll try to see if you can get a little closer to a place where f of x and g of x are closer together. So try 2 more, and then once you've done that, move on. I have 2 more problems for you to try that we will discuss on Monday. All right, so we've worked a good deal, but I want you to try 2 more. These shouldn't be quite as lengthy as the ones that we just did, but will be really good practice. So approximate the real solutions to the system of equations below. And we did an example very similar to this, so you really want to follow that same protocol. And then for 3, 2 functions f and g are graphed below. Find the approximate solutions to the graph f of x and g of x. That's a really quick one, so just go ahead and move through both of these accurately and precisely so that you're ready to move on to some more advanced questions when we meet again.